Every morning, it returns, a familiar, comforting presence in our sky, the sun. It warms our world and gives light to our days. It is the engine of life on Earth. Without it, there would be no plants, no animals, no us. We are, in a very real sense, children of the sun. Its energy travels across 150 million kilometers of empty space to reach us. That journey takes just over 8 minutes. The light that you feel on your face right now left the sun while you were still making your morning coffee. It's a constant, reliable anchor in our lives, a celestial rhythm that has governed our planet for billions of years. We wake with it. We sleep when it departs. Our entire existence is tuned to its steady beat. This star of ours is not just a bright light. It is a colossal nuclear furnace. Its immense gravity holds our solar system together. It keeps Earth in a perfect, life-sustaining orbit. Everything we see, everything we are, is powered by its light. This brings us to the big question. When will this happen? How much longer does our sun have? It's a question that touches on our own mortality, scaled up to a cosmic level. Thinking about the end of the sun forces us to think on timescales that are almost beyond human comprehension. Our lives are measured in decades. Civilizations are measured in millennia, but the life of a star is measured in billions of years. Everything has a beginning, even something as immense and powerful as our sun. Its story starts not with a bang, but with a whisper. It begins in a vast, cold cloud of gas and dust, a cosmic nursery floating silently in the spiral arm of the Milky Way galaxy. This cloud was truly enormous, stretching light years across space. Mostly it was made of hydrogen, the simplest and most abundant element in the universe. But it was also sprinkled with heavier elements. These were the ashes of long-dead stars, scattered into space by ancient supernova explosions. Our sun, and indeed our entire solar system, is made from this recycled stardust. We are the children of cosmic ghosts. For millions of years, this cloud drifted peacefully. But the universe is never truly still. Something disturbed it. Perhaps it was the shock wave from a nearby exploding star, a supernova. Whatever the cause, a small part of this giant cloud began to collapse. Gravity, the great architect of the cosmos, took over. As the cloud collapsed, it began to spin faster and faster. The spinning motion flattened the collapsing cloud into a disk. At the very center of this spinning disk, matter was becoming incredibly compressed. The heart of the collapsing cloud began to glow, first with a dull red heat. Then, the magic moment arrived. The temperature and pressure in the core reached a critical point. Nuclear fusion began. In that instant, our sun was born. The young sun was not the calm, steady star we know today. Its early life was turbulent and chaotic. It spun much faster than it does now, generating incredibly powerful magnetic fields and massive solar flares. The planets were constantly bombarded by high-energy particles. Mercury likely had its early atmosphere completely stripped away. The auroras would have been a permanent and spectacular feature in our skies, visible from all over the globe. Over hundreds of millions of years, the sun began to calm down. Its rotation slowed, its magnetic activity decreased. The star was maturing, entering a more graceful middle age. This stability was crucial for the development of life on Earth. A more stable sun meant a more stable climate, creating the predictable conditions needed for complex life to emerge and evolve. So where does our sun fit in the grand cosmic scheme of things? Our galaxy, the Milky Way, contains hundreds of billions of stars. In this vast stellar population, our sun is actually quite average. It is what astronomers call a G-type main sequence star, or a yellow dwarf. The sun is located in a quiet, suburban neighborhood of the Milky Way, about 27,000 light-years from the galactic center. The center of the galaxy is a much more chaotic place, with a supermassive black hole and much more high-energy radiation. Our sun is also a solitary star. Many stars exist in pairs or multiple star systems, orbiting each other. A planet in such a system would experience complex and unstable orbits, leading to extreme temperature swings. Being part of a single star system provides the stability needed for a planet to maintain consistent orbit and climate over billions of years. While the sun itself may be ordinary, the stability of its circumstances is perhaps less common, creating the perfect cradle for life. At the very center of our sun lies its powerhouse. This is the core. It is a place of unimaginable extremes. The temperature here reaches a staggering 15 million degrees Celsius. The pressure is over 250 billion times the atmospheric pressure we experience on Earth. In this intense environment, matter behaves in ways we never see in our everyday lives. It is a seething soup of subatomic particles, a state known as plasma. The process that powers our star is called nuclear fusion. Inside the sun's core, hydrogen nuclei are forced to slam into each other and fuse together. The resulting helium nucleus has slightly less mass than the original hydrogen nuclei. This missing mass has been converted directly into tremendous energy. Every single second, the sun converts about 600 million tons of hydrogen into helium, releasing energy equivalent to billions of hydrogen bombs. This constant release of energy creates pressure that counteracts the sun's gravity, maintaining the delicate balance known as hydrostatic equilibrium. The energy produced in the sun's core does not reach us immediately. A single particle of light, a photon, begins an incredibly long journey. The photon stumbles through the sun's interior in what is known as a random walk, constantly being absorbed and re-emitted in random directions. It can take a single photon on average around 170,000 years to travel from the core through the radiative zone. The light that warms your face today was generated in the sun's core before modern humans even existed. After its long journey, the energy reaches the convective zone, where hot plasma rises to the surface carrying heat. It works just like a pot of boiling water on a stove. Once in the convective zone, it takes only about a month to travel to the surface. At the surface, the photons finally escape and fly off into space, arriving at Earth 8.5 minutes later. What we think of as the sun's surface is not solid at all. This visible surface is called the photosphere, with a temperature of about 5,500 degrees Celsius. Above the photosphere lies the chromosphere, visible during eclipses as a faint reddish ring. Oddly, its temperature increases with altitude. Extending for millions of kilometers is the corona, the hottest part of the sun's atmosphere, reaching temperatures of 1 to 2 million degrees Celsius. How the corona gets so incredibly hot is a major unsolved problem in astrophysics, likely related to the sun's complex magnetic fields. The sun is constantly breathing out a stream of particles called the solar wind, traveling at over 1 million miles per hour. This wind creates a giant protective bubble around our solar system, deflecting harmful cosmic radiation. Earth's magnetic field deflects most of the solar wind, but some particles create the beautiful aurora. The aurora are a visible reminder of our planet's constant interaction with our star. The sun is the anchor of our solar system, but as we have seen, this stability will not last forever. The sun is a star, and like all stars, it is aging. It is consuming its fuel, second by second. Our sun has about 5 billion years of stable life remaining. This timescale is almost impossible for us to truly grasp. 5 billion years is longer than the Earth has even existed so far. The whole story of our planet has played out in less time than the sun has left. However, the story begins much sooner. The sun is slowly getting brighter by about 1% every 100 million years. Over the next billion years, this gradual brightening will trigger a runaway greenhouse effect. The oceans will boil away. Earth will become a scorching dry world, much like Venus is today. Life as we know it will be extinguished. The story of the sun's aging is a two-part tragedy. Earth's clock is ticking much faster than the sun's. For about 5 billion years from now, our sun will have continued its main sequence life. But now, the sun itself faces its own crisis. The hydrogen fuel at the very center of its core will finally be exhausted. With the core's energy production shut down, the delicate balance between gravity and pressure is broken. The core begins to collapse. As the core collapses and heats up, it ignites a shell of hydrogen around it. A new fire is lit, but this time not in the core. The sun has entered a new phase of its life as a hydrogen shell-burning star, producing much more energy than before. This immense new flood of energy pushes the sun's outer layers outwards. They swell like a monstrous balloon being inflated from within. The sun will swell to more than 100 times its current radius, becoming a colossal red giant that utterly transforms the solar system. As the surface cools, its color will change from familiar yellow to a deep fiery red. Our familiar sun will be replaced by a ruby-red orb dominating the sky. The expanding red giant will finally reach the orbits of the inner planets. Mercury and Venus will be vaporized and consumed. Earth's fate hangs in the balance. The solar system we once knew is gone. A new, vastly different system has been forged, ruled by this monstrous, dying star. The sun's gravitational grip has weakened as it shed mass. The surviving planets have spiraled outwards into larger, more distant orbits. Mars, once the red planet, now orbits a much larger red sun, its own color paled by the star's fiery glare. The gas giants will be bathed in warmth they have never known, causing dramatic changes to their weather systems and appearance. As the sun's destructive fire consumes the inner solar system, a strange thing happens in the outer reaches. The habitable zone pushes outwards to the orbits of Jupiter and Saturn. The once frozen moons of these gas giants are now bathed in gentle, life-giving warmth. Europa's icy shell melts away, exposing its global ocean to the sky. Titan could become a true water world, a place where the building blocks of life might combine in new ways. It would be a second Genesis in our solar system, happening billions of years after the first one on Earth. While the sun's outer layers swell, the helium core continues its relentless collapse. Eventually, it reaches 100 million degrees Celsius. At this extreme temperature, helium fusion ignites in a violent event called the helium flash, generating energy at a rate 100 billion times that of the entire galaxy. This reconfigures the sun's interior. The core expands and the star shrinks, entering a new phase as a helium-burning star. The sun finds temporary equilibrium, but this phase lasts only about 100 million years. When helium runs out, the sun enters its final, most dramatic phase. It now has multiple fusion shells burning simultaneously, a complex layered structure like a cosmic onion. This double shell burning drives the sun's final expansion. It becomes even larger and more luminous, easily engulfing Earth and likely Mars as well. The star becomes violently unstable, shedding its outer layers in a powerful stellar wind. The sun is literally coming apart, layer by layer. These expelled layers form a beautiful glowing shell of gas, a planetary nebula, illuminated by the hot, exposed core left behind. As the planetary nebula expands and fades, the object at its center is revealed. This is what remains of our sun's core, a white dwarf. It contains about half the sun's original mass compressed into a sphere roughly the size of Earth. A teaspoon of its material would weigh several tons. The surface temperature is over 100,000 degrees, glowing with brilliant blue-white light. The sun's life as a star is over, but its afterlife as a glowing ember has begun. The core is locked in a crystal lattice structure, essentially a giant cosmic diamond, a monument to the sun's 10 billion years of stellar life. The white dwarf will now begin the longest process of its existence, simply cooling down. Over billions of years it will fade from blue-white to yellow to red. The surviving planets will continue their journey around this ghost of a star. Their skies will be dominated by a tiny, piercingly bright point of light. Trillions of years will pass. Eventually, the white dwarf will cool to just a few degrees above absolute zero, becoming a cold, dark black dwarf. Over even longer timescales, the solar system will dissolve. The planets will be stripped away, ejected into the galaxy as rogue worlds. We have traveled an immense distance, not across space but through time. We have journeyed from the birth of our sun to its magnificent, fiery death billions of years from now. This story is not a guess. It is a narrative pieced together from observation and the fundamental laws of physics. It is a story written in starlight. The fate of our sun is the fate of all stars of its size. It is a universal story of birth, life, and death. We are, in the most literal sense, made of stars. Our existence is a testament to this grand cosmic cycle of renewal. The story of our star gives us the gift of perspective. We are living in a precious, fragile instant, a brief period of cosmic warmth. This knowledge should make us appreciate how incredibly fortunate we are. The universe is vast and hostile, yet here we exist. We are stardust that has woken up, and for a brief moment, we can look out and understand the cosmic story we are part of. The ultimate fate of the sun is sealed, but the fate of humanity is not. We are a young species, just beginning our journey. So when you next feel the warmth of the sun on your face, take a moment to think of its incredible story. Think of its birth in a cosmic cloud, its long and stable life, and its eventual beautiful death. Think of the immense journey that light has taken to reach you, and the profound fact that you are here to experience it. We are children of the sun, living through its golden age. Our star's story gives us a sense of our past and ultimate future. But most importantly, it illuminates the breathtaking wonder of our present, our brief but glorious moment in the sun.